Hello, I'm Zain Solis,
Hi, I'm Hui He.
and today we'll be describing our paper, Modeling the Hypothalamic Pituitary Adrenal Axis and Correcting the Hypocortisolism case by applying a controller. Chronic fatigue syndrome, or CFS, is a complex disorder that causes extreme fatigue. A few symptoms are memory problems, headaches, and pain in multiple joints. This syndrome is hard to diagnose, and to this day it's not known for certain where it comes from. A group of scholars propose that CFS could be the result of another disorder called hypocortisolism. This is when the body is not producing enough of a hormone called cortisol. Current methods of addressing the hypercortisolism disorder is that a doctor verifies you have a deficiency of cortisol by taking a look at your blood work. Once confirming, the physician may prescribe a patient with cortisol supplements to increase your levels. But when examining science from an engineering perspective, we find that this may not be a long-term solution and just a temporary aid to the problem. From bridging these two worlds together, we propose a different solution. Let's take a look at how hypocortisolism develops in our body. The hypothalamic pituitary adrenal axis, also referred to as the HPA axis, is a major system of our bodies whose outputs contribute to a range of systems, from the functionality of the sympathetic nervous system to the digestive system to our immune system response. It is directly related to hypercortisolism. The HPA axis is made up of a three-part group: the hypothalamus, the pituitary gland, and the adrenal glands. The HPA axis ultimately keeps the body in an equilibrium state by adjusting other systems to changes to the body internally and externally. The HPA axis senses stressful situations. This could be one of physical harms such as cuts or burns, or mental in the sense of lost loved ones or being deployed in a war for a long time. This system begins with the hypothalamus. It senses when there is a stress that is put on our body. This activates the paraventricular nucleus of the hypothalamus to release corticotropin-releasing hormone, known as CRH. This hormone will flow through the pituitary stalk down to the receptors on the pituitary gland. This reaction initializes the gland and causes the secretion of another hormone, adrenocorticotropic hormone, or ACTH. ACTH travels through the bloodstream all the ways down to the receptors on the adrenal glands. The adrenal glands are now activated and release glucocorticoids, which is many types of hormones. For this study, out of the glucocorticoids, we are only interested in the cortisol hormone. Cortisol binds to the glucocorticoid receptors. These are found in every nucleated cell. The result of this gives an effect on almost all systems. In terms of the stress we are presented with, the cortisol hormone allows you to be tense, alert, and have enough energy to address the situation. Lastly, the cortisol acts back on the hypothalamus and the pituitary gland to let the system know that there is enough cortisol being produced. This then suppresses the production of CRH and ACTH hormones. From the medical background mentioned above, we can translate the HPA axis into a control system theory. Our input into our system is stress. The first subsystem that receives this input is the hypothalamus. Its output, CRH, inputs to the pituitary gland, and its output then inputs to the adrenal glands. The final output is cortisol. But there are two negative feedbacks going back to the hypothalamus and the pituitary gland. It's a good time to note, under normal circumstances, meaning your body is feeling no stress, the HPA axis system is continuously producing a small amount of cortisol. This is because other parts of our body and other systems need some cortisol to function properly. This means the system is running continuously just at a very minimal rate. We call this small amount of cortisol being produced the equilibrium amount. Mathematically, we refer to it as the equilibrium point. The problem that arises is if the body continues to receive an input of high stress over a long period of time. The system will lose its healthy equilibrium point. What is meant by that, when stress is removed, the system will settle at a new equilibrium point. This point could shift high, meaning under normal circumstances your body will produce more cortisol, or the point could shift lower, thus producing less than the body needs on a normal basis. For this particular study, we'll be looking at the scenario when stress is applied to the body for a long period of time and the equilibrium point is shifted lower than normal. This is called hypocortisolism. To do any study that involves the body, it requires a great amount of knowledge, countless time of testing, simulations, and clinical approval and trials in order to be applied to human lives. Therefore, our work is just an in-depth study of two groups of knowledgeable scholars who have previously proposed a complex state-space model of the HPA axis and a correction to the HPA axis dysfunction using modern control theory. The nonlinear mathematical model of the HPA axis we'll be using incorporates a modern state-space oriented system. It was presented by Gupta et al. In the article Inclusion of the Glucocorticoid Receptors in a Hypothalamic Pituitary Adrenal Axis Model Reveals Bistability. This model is a more accurate model of the HPA axis. From our other set of scholars in the article Model-Based Therapeutic Correction of Hypothalamic Pituitary Adrenal Axis Dysfunction, the proposed solution is one that is counterintuitive and requires optimal control. The goal in our report is to model the HPA axis, linearize the system around certain crucial points checking controllability, observability, and stability. Lastly, we'll apply a controller to the HPA axis system to correct the unhealthy state of cortisol. The majority of this work will be computed and designed in MATLAB.
What we call systems, whether physical, like the spring mass system, physiological, this example of gene interaction, or even non-physical, are described and studied by differential equations. These equations contain the states, which can be displacements, angle, velocity, etc., and their rates of change, which we call derivatives, to translate the dynamics or behaviors in time, space, or both. Although they are challenging from having many classifications and difficult solving procedures, they are powerful tools allowing us to compute, understand, analyze, and design solutions for whatever problem we're facing with. With modern control theory branch of engineering, state-space models using matrices representation help simplify further the analysis of differential equations. And the way you read these models is through matrix multiplication and addition across all rows and columns. Gupta et al. Derivation of human HPA system presented in state-space form comes from the understanding of its three organs communicating with each other through hormone interactions, as described in the beginning of the introduction. Initially, Gupta et al. Represent the three organs of the HPA system by their linear behaviors of constant production and degradation of the primary corresponding chemical hormones, CRH from the hypothalamus, ACTH from the pituitary gland, and cortisol from the adrenal gland. This means that any time our body produces and removes the hormones in a graphical straight line manner. Linear dynamics are easy to analyze but most of the time not accurate in representing real life situations, especially for the human body. For that matter, the glucocorticoid receptor dynamic in the pituitary gland was incorporated into the model equations. GR is a decent candidate in improving the model accuracy because, despite its complex nonlinear synthesis process, it is the principal regulation agent of the ACTH production. In other words, while cortisol provides the negative feedback signal to the pituitary gland, these GR are responsible for quantizing the error and downregulating ACTH, ultimately cortisol as well, to maintain homeostasis. GR synthesis and nonlinear regulation of other hormones now reveal an inherent bistability of the human body after a long-term exposure to intense stress. To show the robustness of the model, the cortisol production degradation equation was plotted using MATLAB and compared with Dr. Leslie Crawford's human serum cortisol data of patients suffering from chronic fatigue syndrome. We can see that the two lines closely match with each other. Next, we focus our work on the control effort proposed by Amos et al. In correcting the HPA axis dysfunction. Amos et al. Claim that the second steady state does not only exist on theory, but is also compatible with clinical observations of patients' cortisol concentration level suffering from CFS. By taking advantage of the system new dynamics and adopting the model predictive control framework, which revolves around defining a clear objective function for measured variables and optimizing control efforts to avoid dangerous behavior of system by the application of control action, they augmented the model with the control term U of t, manipulating the rate of removal of cortisol from circulation. First off, we want to analyze the initial system without the U term using the control theories learned in EC 5335 to develop insights which could potentially lead to understanding the logic behind Amos et al. Controller design. Upon inspection, we see that the system is a nonlinear but time invariant, which means the analysis techniques studied in class are not readily applicable. Instead, we need to determine the equilibrium points of the state space model. With the linearized model, controllability, observability, and stability analysis can be computed using the matrices A, B, C, and D. At this point, perhaps controllability and observability do not greatly contribute to the controller design, due to the fact that we're trying to move the system from one steady state to another, which is a nonlinear effort. Inversely, stability of our linear model brings extra robustness to the controller design. A stable linear system guarantees its steady value convergence to or around the equilibrium point around which it had been linearized. In the effort of redirecting the HPA axis, we want our model to converge back to the healthy state as it leaves the unhealthy region responding to treatment. Now we look at the augmented system, which simply has a U of t term added to the fourth equation of the set. Usually, the term U of t is used for input to a system or the error signal to be corrected. In the case of our HPA system, U of t is the actual controller designed to shift the system from one steady state to another by artificially reducing cortisol concentration using some kind of medication. The logic behind such design is that Gupta et al. Model can accurately capture the shift of GR synthesis at an increasingly higher stable steady state, ultimately reducing cortisol level to a lower unhealthy state in response to chronic intense stress. It is also possible to reverse the system dynamics by going the opposite way. And with the stability analysis we have seen earlier, this is rather a robust approach. However, disturbing a system with nonlinear dynamics is delicately difficult and may highly produce unpredictable results. And here we are dealing with the human system. For this reason, Amos et al. Chose an optimization problem, or solving for the optimal control effort, to prevent any dangerous destabilization of the HPA axis while adapting to the treatment. An optimal control problem usually translates into minimization of a defined objective function with constraint. A general objective function includes the matrix Q for the state vector x and the matrix R for the input vector U, where Q defines the weights on the system states and R the cost of the input. The author's result penalty function is by setting R equals 0, meaning the cost of treatment is not comparable to the success of the treatment for patients, and with the assumptions that since CRH and GR are not readily measurable, the penalty will reflect in the change in ACTH concentration. However, the optimal solutions computed by computers are not easily implemented in the clinical setting. A suboptimal treatment as a constant straight reduction of cortisol in time is proposed instead.
By setting the four nonlinear equations of the HPA axis system equal to 0 and incrementing our stress factor d0, we were able to see just how the system behaves over a range of stress. This is shown in this figure. We can now see that there are multiple solutions in the range of stress being negative 0.02 to 0.8. Make a visual note of how the blue signal cortisol behaves. Described earlier, we can now see how a chronically stressed individual's cortisol levels of healthiness, the green dot, would shift following the red line as you increase stress, and when stress was taken away, would settle out at the new unhealthy cortisol level, the red dot. In order to reset back to normal, it is proposed that we control the level of cortisol along the path of the green line. Now we will redirect the HPA axis to the healthy state. The optimized input U of t is a calculation done multiple times on the system until ACTH increases to 30% above its initial point and the level of cortisol is driven back to the healthy state. From the optimized U of t, we draw a suboptimal input seen here. Results of applying this new input to our system can be seen here. We see that ACTH increases to about 30% higher and our state variables steady states go back to a healthy person's equilibrium points. We'd like to state, while the models and math do work, this is only for an ideal case, not realistic. But for simplicity of testing our system and control, we set certain variables constant. For example, stress being 0 during the treatment is one setting that is not true. The patient's level of stress is uncontrollable of setting. Thus, the initial point of cortisol in your body system changes person to person. Another ideal assumption was that cortisol is released into the body at a continuous amount. Cortisol is actually released more as multiple impulses for a small amount of time, with durations ranging in time. Again, though for simplicity, we assume cortisol to be continuous.